Hey everyone, this is Chris Dingman, Math and Science Explainer Raterer, offering private online tutoring. And this is my second video about functions. Following up on the introduction, in this video I'm talking about how useful functions can be by giving you some examples that's really going to solidify your idea of what a function is. And I'm also going to talk about inputs and outputs and how they can be switched around and how functions can be written in different ways. Okay, let's dive right in. So here we go. Let's write the magic word down. In the last video, we said that a function is essentially a rule, such as multiply a number by 2, add 6, then divide by 8, square a number, leave the number alone, etc. Now, let's talk about why this might be useful. And let's start with a simple example that you really don't need a function for, but it's something I think most of us can picture, so it's nice and simple. For instance, let's say you're driving a car. And you're going 50 miles an hour. Okay? And you want a function where you input the time and output how far you've gone. In other words, the distance. So you want to know, I've driven 6 hours. How far have I gone? So your function is a useful little box or machine where you tell it the time and it tells you how far you'll get, the distance. Now, a lot of you have probably seen this function written. We can write it. Let's use d for distance, right? You're always going to need variables, and usually it's nice to have the variable start with the letter of the thing it refers to. So it's going to be d equals 50 times time. We can just say 50t. That means times time, right? Because if I go 1 hour, in other words, I input a 1 for t, and I'm going 50 miles per hour, or every hour, my distance will be 50 miles. Okay, or I could input a 2 for time. So I simply substitute 2 for the letter t, because remember, t is just a place. It's a place to put a specific number. And then we have d equals 50 times 2, or 100 miles. And of course, you could probably do that in your head without having to write a formula out, but I'm just doing this to illustrate. And you might not be able to do in your head, for instance, say I drove 1.75 hours. The formula could come in handy there, so 50 times 1.75. All right, we might need to get our calculators out. I'll do that now. Distance equals 87.5 miles. Right, so that's a little more handy. You can see that the formula or equation or function would come in handy there. And by the way, function, equation, and formula all mean really the same thing in this context. We're just talking about that. Okay, now at this point, I want to mention something that's true about every function, and that is this idea of input and output is not so set in stone, because I actually could do the reverse. I could input the distance in this case and output the time, right? We can imagine asking, okay, I want to drive 400 miles from San Francisco to LA. Don't know why you'd want to go to LA, but um, uh, and we could say I want to drive 400 miles, and I want to know how much time it's going to take. So this time we're inputting the distance. How would that work? Well, let's write the formula or equation or function. All right, so LA is about 400 miles away, so I'm going to put in 400 for the distance, right? Again, D is the placeholder. It's a place to put a number. And now I've got this. Now, you may know how to solve equations, you may not, you may anywhere in between, but we can solve this equation for t. In other words, we can figure out what t is. And I'm not going to get too much into solving equations in this lesson, so if you know how, great. If you don't, just trust me. You would divide both sides by 50, and that would cancel out the 50, and it would just leave the t by itself. And then on the other side, over here on the left, you would go 400 divided by 50. That's 8. So look at that. I was calling d the output and t the input, but you can actually input in either spot. If you want to input for the d, you just have to this time do a little rearranging or work or equation solving to get your t value. In other words, this function, this equation, is set up so that it's more convenient to think of d as the output. Because notice I stuck in a number, and it was just a matter of multiplying and getting the answer, multiplying and getting the answer. So it was just easier to think of t as the input, or to input a t. But we certainly could input for d and then find t. And you can do it. You can just, every time you have an input of d, you can just put it right there and do what we did, solve for t. You can also rearrange this formula so that t is the output and d is the input, or it's more convenient, right? So what would that look like? What that would do, or how we would do that, is we would take the original equation, and we would basically do what we did over here, except we wouldn't have a number. So I'm going to divide both sides, and well, we wouldn't have a number for d. I'm going to divide both sides by 50, just like I did over here. And the 50 is still going to cancel out. And I'm going to get t equals distance divided by 50. And then I like to have my single variables on the left. So I'm just going to flip it around, which is perfectly legal in most states. And I'm going to have time equals distance divided by 50. Okay, so we have the same relationship between distance and time. This is really the same as this. They're really called inverse functions of each other. Don't worry about that right now. But one is written so that it's easy to input the time and output the distance. That's this one. And one is written so that it's easy to input the distance and output the time. The bottom one. Okay, but once again, no matter which way you write it, okay, I'll say this as the first way, 1 or 2, no matter which way you write it, you can always input either variable and then solve for the other variable. Okay, so functions can be rearranged so that one variable, any variable you want, is by itself. At least in most of high school math, it's going to be possible to what we call isolate or solve for that variable. And those, by the way, are good terms to know. when someone says solve, if someone said solve this equation for t, you would do this. What that means is isolate that variable. And what it also means is treat that variable like it's the output. Okay, so that's really good little thing to keep in mind. Let's look at another function that's something useful in everyday life and a little bit more complicated than this one. And that is the function for changing Fahrenheit to Celsius and vice versa. Okay, so Fahrenheit, which I'm going to call F, is equal to the degrees Celsius times 9/5, or 1.8 if you're a decimal kind of person, and then you're going to add 32 to that. Now, does this treat Celsius as the input or the output? It treats Celsius as the input, right? Because whatever's isolated over here, we can think of as the output. Again, it doesn't have to be the output, but I should be saying it's more convenient. It's in the spot where it makes it convenient to be the output. So again, let's look at why that is. Let's say you are traveling in Europe, if you're American, and you're told that it's going to be 25 degrees Celsius. Well, that sounds cold, but it isn't. So let's see what it is. We put in a 25, because remember, the variable is a placeholder. It's a place to put a number that you don't know yet, and it's called a variable because it varies. So 25 is our input, and the function in this case is a rule that multiplies the input by 9/5 and then adds 32. So 25 times 9/5 is, I can do some canceling here, is 45. And then we're going to add 32 to that, and we're going to see that that's 77 degrees. So input a 25 right here, substitute 25 for the variable c, output a 77. Notice we did not have to solve anything. We didn't have to rearrange variables. F just sat out here the whole time as the happy little output. If we knew the Fahrenheit, okay, so you're a European traveling here, and someone said it was going to be, let's say, 50 degrees Fahrenheit, that's going to sound incredibly hot to you, but it isn't. So, like we said just recently, you could put the 50 degrees here. You could input it in what is sort of the output slot. And then you'd have to solve for C. You'd have to essentially move all these numbers over and get C. Now, I think for the purposes of this video, I'm just going to tell you what it would look like to rearrange the function so that it's more convenient to have C as the output and F as the input. Okay, so what does that function look like? That looks like this. C is equal to Fahrenheit minus 32 degrees, and then after you get that answer, you're going to multiply that. I won't use the times sign. I'll use a dot. You're going to multiply by 5/9. So don't worry about this too much here, but you can kind of see that we're kind of reversing things. Here we added 32. Here we subtracted. Here we multiplied by 9/5. Here it's that fraction flipped over. But we're not going to worry too much about that. The important thing here is that now we've rearranged the equation so that it's more convenient to think of F as the input and C as the output. So here we're going to input 50 for F. C is going to equal 50 minus 32 is 18. And then 18 times 5/9. Let's do some canceling. 2 times 5 is 10. So 50 degrees Fahrenheit is 10 degrees Celsius. But again, I actually didn't really need this second way of writing it, because I could have just put the 50 here and then figured out what C is by solving the equation. So that's essentially what I wanted to cover in this lesson. I will show you, if you want to stick around, I'll show you one more function that you see a lot. They use it as an example in math a lot, and it's also something you'd see in physics. So feel free to stick around, and I'll just show you that function real quick. This is a function used to calculate the height of an object that is thrown, kicked, dropped on planet Earth. So it has to take into account the strength of gravity, how fast you threw it, shot it out of a cannon, whatever it might be. So that's going to be called the initial speed or velocity. Let's use the velocity. And then the other thing you need to know is how high you were when you dropped through, etc., the object. So your initial or starting height. So there is a function that inputs the time. So time is input, and outputs the height. Let's make that yellow. Output. Okay, so that's height, and this is time. Now, the initial velocity is going to vary, and so, of course, is the height, but gravity is actually, on the surface of the Earth, is going to stay constant. And if we do this in feet, actually, let's do it in meters so that we can include our non-American friends. The formula is going to be the height is equal to negative 4.9. Actually, let me make that blue because I did gravity in blue over here. Negative 4.9 t squared plus the initial velocity. Okay, let's make that pink. Initial velocity, VI for initial velocity, also times the time. And then let's say we'll make the initial height purple, so plus the initial height. So let's say you threw a ball at, I don't know what a realistic speed is, 20 meters per second. So that's your initial velocity, is 20. And let's say you threw it from 3 meters off the ground. So that's your initial height of 3. Now, you don't get a choice about gravity. Gravity is a certain strength, and the number there that's going to make this formula accurate is negative 4.9. Okay, so that means we now have, for this particular situation where you know the 20 and the 3, we're going to have h equals negative 4.9 times the time squared plus initial velocity, you threw it at 20, again times the time, plus the initial height of 3. There's your function. Ignoring air resistance or wind or anything else, this would do a pretty good job of telling you how high the object you threw is going to be at a certain time. Right? So at the time you threw it, well, right before you threw it, that's time 0. So if you put in a 0 for time, you're going to get This is 0, this is 0, because anything times 0 is 0. Height is 3. Well, that's no surprise. That's just saying you started at 3. So that's not very interesting. But we could do like a second later, 1 second after you throw it, where would the ball be? You can see this is kind of complicated because you threw it with a certain speed, but gravity is immediately slowing it down. But anyway, the point here is just that you can input 1 second in the t input slot, and this handy function is going to output you the height of the ball. Okay, 1 squared is 1, 4.9 times 1 is 4.9, 20 times 1 is 20. So negative 4.9 plus 20 plus 3 is going to be h equals the ball's going to be 18.1 meters off the ground. Then again, we could think of inputting a height and outputting a time. So for instance, instead of saying I want to know how high the ball is after 1 second, so input 1 for time, I could say I want to know what after how many seconds, in other words, at what time, the height is going to be 0, meaning back on the ground. So let's actually make a little diagram at this point. So here you are on your platform that gives you your starting height of 3 meters. There you are throwing the ball. Okay, and then the ball's going to come back down. And the question was, so this is height 0, right? When it hits the ground, that's a height of 0. So how much time does that take? Well, you would just input 0 now for the h. So what used to be the output is now the input. You'd put in a 0 for h, and you would solve this and figure out what t is. Now, that's a little complicated, and we can get into that in another video. And actually, I think I talk about this in my video about quadratics and parabolas, so you can find that series and have a look at that if you want. Point being here, just another function with inputs and outputs that is useful in real life. Okay, in the next video, it's going to be short. I'm going to talk about function notation, what we call things like f of x. You may have seen that before. It may have confused you. I'm going to go into that. It's really simple. You're going to understand it. Okay, see you in the next one.